Okay, so for the cross product, we need to evaluate determinant. So that's what we're going to do. The prerequisite skill first, evaluating a 2 by 2 determinant and a 3 by 3 determinant. So the 2 by 2 determinant, it's fairly easy to evaluate. All we do is multiply the elements of the matrix along the main diagonal, that is A times D, and subtract the product between the elements along the secondary diagonal. So the main diagonal is going to be the diagonal that goes from left to right, while the secondary diagonal is going to be formed by the element that go in the backwards direction, B times C. Okay, so this one is easy to evaluate. The 3 by 3 matrix, that's the one I'm worried about, because you may have learned this method right here, which is the expansion by cofactors and minors. Again, those of you who already took linear, you know what's that. But also in pre-calculus, you may have learned this way as well. But I'm going to show you a different rule to compute, because on your sheet of notes for the exam, you may want to save space and not write this huge formula, all right? And actually, computing the 3 by 3 determinant, it takes longer doing this method. And the method I'm going to show you, it's a lot quicker. Well, number one, let's evaluate each determinant here. So, and again, 4 times 1 minus, so 4 times 1 minus negative 3 times 2. That's 4 plus 3 times 2 equals to 6, which equals to 10. So that's the determinant, that's the result of evaluating this 2 by 2 determinant. Okay, what about the 3 by 3 determinant? Honestly, I don't want to do this big formula. I have to put it on the notes because actually that's what the book uses. And when you're doing the homework, when you look at the view and example, that's what they're going to do. Use the expansion by cofactors. Okay, how does the shortcut? Well, it's not really a shortcut. It's actually a rule, and there's a name for that. It's called Sarus rule. These Sarus rules consist of duplicating the first and the second column. So repeat the first and the second column. And this is what we're going to do. So I'm going to evaluate the products of the elements along the 3 main diagonals. What are the 3 main diagonals? Check this out. Okay, so 2 times 7 times 5. Okay, what is that going to be? 2 times 7, is that 21? 21 times 5, is that 70? So that's 70. I'm going to group those numbers. 70. Okay, the second main diagonal, that is negative 3 times negative 2 times 4. I have 24. So plus 24. And 1 times 3 times 0. Well, plus 0, that's going to reduce some work. Okay? I'm going to subtract the products of the elements along the remaining secondary diagonals. That is, okay, minus negative 3 times 3 times 5. Okay, so that's 3 times 3, that's 9 times 5. Is that 45? Negative 45. 2 times negative 2 times 0. Whoa, that's a 0. That's great. And 1 times 7 times 4, that's 28. And that's a lot quicker than evaluating 3 2 by 2 determinants. All right? A lot quicker. Okay, so 70 plus 24 plus 0, is that 94? Minus, careful. Number 1, let me do negative 45 plus 28. That's minus negative 17. And add. All right? That's a 94 plus 17. That equals 111. Okay? So we're going to use this rule to evaluate 3 by 3 determinants to find the cross product between two vectors, because, well, Um, Unlike the dot product, this cross product is not just multiplying the component wise all the elements of the vector, the components of the vector. No, in this case, it's we need to set up a 3 by 3 matrix, and where the first row it's the standard unit vectors I, J, and K, and the remaining two rows are the given two vectors that we want to find the cross product of. Okay, so if we're given two vectors u1, u2, u3, v1, v2, v3, the cross product, there's two definitions. In a similar way that we got a definition in terms of trigonometry, however, in this case, it's going to give us the magnitude of the cross product, and it's going to involve the sine function, not the cosine function like in the dot product. Okay, and the other way to get it is by evaluating this determinant. And again, this is the formula I have to give it. It's from the textbook. It's what you guys are going to see on MyMathLab when you click on view an example. But again, I'm going to use the Sarus rule to evaluate this quicker. Okay. However, if you still prefer to evaluate it this way, well, that's fine. I don't have a problem with it. Okay, that's fine. So, how about we find some cross products here? Okay, so U cross V. And notice in this case they're giving us the vectors as a linear combination of standard unit vectors I, J, and K. Okay, so I'd rather change those vectors to component form. Okay, I'll show you why I prefer component form as opposed to this form. You'll see why. So this second vector, so oftentimes we are reading a problem, we're in a hurry reading a problem, and it's very easy for us to make silly mistakes like the one I'm going to do. V, which is 2, 5, 0, right? Because there's two terms, one of them has to be 0. But I didn't stop and analyze this vector. Actually, the missing component is the I component. So really, the correct vector is 0, 2, 5. All right. And I've seen a lot of silly mistakes on exams and quizzes because of this. So my advice: you're given linear combo notation for vectors, change them to the component form instead. Okay, so let's denote U cross V. That equals, okay, let's set up I, J, K, and set these two vectors as rows. 2, 3, -1, 0, 2, 5. So I'm going to use the trick to repeat by repeating the first two columns. Okay. That is I, J, 2, 3, 0, 2. Okay, let's do the product along the main diagonal. So I times 3 times 5, that equals, okay, 3 times 5, that equals 15I. So 15I. J times -1 times 0, that's easy, 0J. I'm going to write it just for the sake of the notation. And lastly, K times 2 times 2, that's 4K. I'm going to subtract whatever we get from the reverse diagonal, so the secondary diagonals. So that'll be J times 2 times 5, that's 10J. And, okay, what's next? Okay, I times -1 times 2, that's a -2I. And lastly, K times 3 times 0, that's 0K. So all we're going to do is combine I's with I's, J's with J's, K's with K's to get the new vector, which will be the cross product. All right. So I's with I's. 15I minus minus, that's a plus 2I. that's 17i. For the j, 0j minus 10j, that's a negative 10j. And for k, 4k minus 0k, that's simply 4k. And in component form, I'm going to go back to component form, that's 17, negative 10, 4. Right? So that's, notice again, the result of performing the cross product, it's another vector, not a scalar, unlike the dot product. So that's why we call it the vector product, not the scalar product like before. All right. So how about some properties of the cross product? Very important. So you'll see how these properties are going to be a lot different than the properties for the dot with the dot product. Okay, so again, we will consider three vectors: u, v, and w. Okay, in space, by the way. Actually, so here is the thing. The cross product doesn't work with vectors in the plane. That's because, okay, check this out. I, j, say 1, 2, 3, 4. We cannot evaluate, there's no such thing as a determinant of a rectangular matrix. The determinant is only for square matrices, 2 by 2, 3 by 3, 4 by 4, n by n, not when the number of rows and the columns are different. So that's why it's not it's the cross product. It's not defined for vectors in 2D. However, later on we will do it. We will do a trick. Actually, what's the trick? Put in the k, make the z components equal to 0. That's gonna do the trick, right? But I mean, in general, if you were to simply try to evaluate the cross product between two vectors that are in the plane, because of restrictions of the determinant, we can't. All right. A and B are scalars, are multiple scalars. So here's the thing. The order of the product matters when it comes to the cross product. So in other words, the cross product is not commutative. All right? So if we evaluate this cross product the other way around, right? If we evaluate it the other way around, we will get the same components but with opposite signs. And that actually has to do with the properties of determinants. For those of you who have taken linear algebra, or actually you may have seen this in pre-calculus when you learn about determinants. When you interchange two rows, that changes the sign of the determinant. So that's the reason. If we cross product a vector times a scalar with another vector times another scalar, we can multiply the scalars, have them outside, multiply together, do the cross product rather, and then once we're done, we just multiply by the product between A and B. Another distributed property: U cross V plus U cross W, U cross V plus U cross W, or minus. Either way, it works for the plus or the minus as well. All right, either way. The cross product between a vector and the zero vector, no, it's not the number 0, the zero vector, that's the only case where the multiplication is commutative, all right? And the cross product of a vector with itself is the zero vector, not the zero number, the zero vector. Okay. Geometric properties. How are we going to use the cross product? Because we're going to use it for a bunch of things. Okay, number one. What about that new vector we just obtained? So it turns out that the vector we obtained right here, this vector happens to be orthogonal to both U and V, right? That means, okay, let me use the markers right here. So, if these are two vectors right here, so these two vectors do not have to be perpendicular. It can be like this. So the cross product between the two vectors is going to be a vector that is orthogonal to both. Notice how it's orthogonal to the gray vector and the other blue vector, right? But these two other vectors do not have to be necessarily orthogonal, all right? What else are we going to get from this? Okay, so actually this is another alternative to find the angle between two vectors. This rearranging this definition allows us to obtain an alternative to the angle between two vectors. However, here's the thing: we won't use the signed version. That's because of the domain restrictions between the inverse cosine and the inverse sine. So while okay, while the inverse cosine is defined in the first two quadrants, that is cosine inverse of x, the inverse sine, notice how it is defined in quadrants 1 and 4. That means if we use the inverse sine version to find the angle between two vectors, number one, we can potentially obtain negative angles. And well, we don't use negative angles in between two vectors because it doesn't matter the position of the vector. So does that look like a negative angle for you? I mean, a negative angle would be like a negative distance. Do negative distance make sense? Same with negative angles. I know, if this is the positive x-axis and we have the vector like this, yes, the angle is going down, so that should be, yes, negative, but not when it comes to vectors. And then the other disadvantage, of which is more important, do you feel like computing a cross product to find the angle between two vectors? The cross product takes a lot longer to compute than the dot product, isn't it? So that's why we prefer the dot product version for the angles rather than the sine. And I mean, I still have to put this just so we can discuss why the former formula is better than the new one formula. Okay, so the dot product between the cross product between two vectors is the zero vector if and only if the two vectors are multiple scalars of one another, and the magnitude of the vector we obtain out of the cross product is going to give us the area of the parallelogram spanned by the vectors u and v. So here we have a picture. So let me expand this picture like this. Notice how these two vectors form a parallelogram. So the magnitude of this vector that we obtain is equal to the area of this parallelogram. So we can use cross product to solve some geometry problems, right? And what else? Oh, the right hand rule. So the way the right hand rule works is like, so here's the two vectors again. The right hand rule works this way. If I twist my hand in this direction, where is my thumb going to go? Up or down? Up. So that's why we have that vector pointing up right here, right? I suppose that if I do the cross product using my hand like this, where is my thumb going? Down. Do you see why now there's a difference in the cross product? The order matters. So u cross with v is going to be the vector pointing up, while v cross u is going to be a vector pointing down. Yes, basically the same vector, but with the components with opposite sign, which is not the same vector essentially. So that's why the cross product is not commutative. Okay. All right, so another pattern, well, before getting into the applications of this, into the applications of the cross product, let's have a look at a pretty cool pattern here. So, okay, find the cross product between of the unit vectors I and j, and then we'll see a pretty cool pattern. So number one, I equals to 1, 0, 0. And j equals to 0, 1, 0. Well, actually, you know what? I'm not going to compute the 3 by 3 determinant. It's going to be a lot of writing, and a lot of, it's going to take longer. Actually, I'm going to take the geometric approach. I'm going to take the right hand rule approach. So I'm going to do my best to plot this in space. Okay, so this is the x-axis, the y-axis, and the z-axis. Okay, so the vector I is going 1 unit in the x direction. Okay, so this is I. And vector j is going 1 unit in the y direction. Now, think about it. Put your 3D glasses on and think about what will be the result of doing the cross product between I and j using the right hand rule. 1z, right? Is it gonna go up or down? Up, right? Okay, again. This is positive. This is positive. I'm going in this direction, thumbs up, right? So I cross j will be k, all right? So from here, I'm going to get the following circle. Check this out. So triangle, circle. Yeah, it's kind of weird. Okay. We're going to go in alphabetic order, if you will. Check this out. I cross j. What's the next one? Equals to k. What if I wanted to find the cross product between j and k? What would that be equal to? I. All right. What if I wanted to find the cross product between k and I? J. Okay, let's analyze the opposite direction. Let me go about j times I. Okay, j times I again. They're both positive vectors. Instead of going I cross j, I'm going to go j cross I. Where's my son going to go? Down, all right? Okay, so yes, still j times I equals to negative k. I times k equals to negative j, and k times j equals to negative I. So if you multiply the vectors in the clockwise direction, you get the next letter in the triangle with positive sign. If you multiply them in the counterclockwise direction, you will get the next letter in the triangle, but with the opposite sign, but negative. All right. All right. Consider the vectors u2, 1, negative 3, and w, negative 1, 5, 3. Find the unit vector that is orthogonal perpendicular to both u and w. So every time they're asking us to find a vector that is orthogonal to two given vectors, we need to do the cross product. That's because by definition, the cross product of two vectors is a new vector that is orthogonal to the two given vectors. So let's find u cross w. That is I, j, k, 2, 1, negative 3, negative 1, 5, 3, and I'm just going to give you the result. I don't want to spend a lot of time doing the cross product. I think you guys know how it works, how to repeat the two columns, or use the definition. So that's going to give us the vector 18i minus 3j plus 11k. In component form, 18, negative 3, 11. But this is just a vector. This is just another vector. Notice they're asking us to find a unit vector. How do we get a unit vector again? From a given vector. Divide by its magnitude, right? So let's find the magnitude of u cross w. So that'll be in the square root of 18 squared plus negative 3 squared plus 11 squared. That equals, what's that? Square root of 454. All right. So now, to obtain a unit vector, call it V with a hat to denote that this is a unit vector. This will be 18, negative 3, 11 over the square root of 454. Alright, so that'll be 18 over the square root of 454 negative 3 root of 454 and 11 over the square root of 454. Alright, so that's a unit vector that is orthogonal to both U and W. So there's a part B. Find the area of the parallelogram created by or spanned by the vectors U and W as adjacent sides. And that is, okay. So of course I'm not going to plot the vectors in space. I'm just going to do a representation. Alright. So in this case, so this is going to create the following parallelogram, right? So they're asking us to find the area of the parallelogram. Now, how do we find the area of the parallelogram? Okay, let me go back to the previous page real quick. That is found by finding the magnitude of the vector obtained from the cross product. But it turns out we already have the answer, don't we? We did it in part A. We found the magnitude. So area of the parallelogram equals the magnitude of U cross W, which is the square root of 454 units. And could be meters squared, feet squared. We don't know the units, right? We don't know. All right. Okay, so for one more example, a triangle. Okay, now we're going to find the area of a triangle. A triangle has vertices at A, B, and C, given by those three order triples. And they're asking us to find the area of the triangle A, B, and C. Okay, how are we going to do this? Another very classical one. So let me plot this triangle A, B, C. It's going to look like this somehow. So that is A, which is 2, 4, 1, B, which is 0, 3, 1, and C, which is 2, 0, 5. Alright? I mean, somehow we have to use the cross product between two vectors. But and then find its magnitude, but actually that's going to give us the area of the parallelogram, not the area of the triangle. Now, we don't have two vectors, however, we have enough information to obtain two vectors out of 3 points. And you have many options for this. I'm going to go by defining the vector AB and the vector AC. All right? Then that's going to give us a vector that is going to be orthogonal to those two. Well, from the screen perspective, that'll be a vector pointing out of the screen, right? If we compute the cross product in this direction, right? Otherwise, it's going to be a vector stabbing the screen in this case. Okay, but still, even if we find the magnitude of the cross product between those two vectors, that's going to give us the area of the parallelogram, not the area of the triangle. So this is what we're going to do then. We're going to find the area of the parallelogram and divide by 2. That's going to give us the area of the triangle. All right? Let's do that. Okay. So let's define vectors AB. That is 0 minus 2, that equals -2. 3 minus 4, that's a -1. 1 minus 1, that's 0. Again, terminal minus initial. Vector AC. 2 minus 2, that's 0. 0 minus 4, that's a -4. 5 minus 1, that's equal to 4. Okay? So we have two vectors get the cross product. That's going to give us a vector that is orthogonal, and the magnitude of that vector is going to be the area of the parallelogram, then divide by 2 to get the area of the triangle. Okay, let me set up the cross product. I, J, K. So the vectors are -2, -1, 0, 0, -4, 4. And that's going to give us the vector -4, 8, 8. All right. Again, I'm skipping the steps for the cross product, okay, just to save some time. Okay, let's find the magnitude of the cross product. AB, AC. Even if you do AB or AC, AB the other way, you would get a vector with components with opposite signs. But we're going to find the magnitude of that vector anyway. That involves squaring those components. That's going to make them positive anyway. All right. Plus the magnitude is always a positive number. So it doesn't matter if you do the cross product the other way. So that's a -4 squared, 8 squared, 8 squared. That equals, what's that? It's a nice number, by the way. That's a square root of 144, which is equal to 12. All right. Okay. Now that we found the area of the parallelogram, we find the area of the triangle by computing 1/2 the area of the parallelogram. That is 1/2 times 12 equals to 6 units. All right. All right. Applications of the cross product to physics, to torque. Okay. So torque is it's a twisting force that causes rotation, and you've seen that in many different settings. For instance, okay, let me pause this for a bit. So, for instance, when we have this vector, so some distance vector, some length, like a table, again. But then we apply some force. But it's not anymore going to be along the length of the table or whatever the object we want to move, but actually from the side. So we're going to cause a rotation of the object. All right. So a very classical example, and when we go, let me go to the door. So sometimes we're in a hurry and we want to, and I just do this. I'm going to struggle to open the door a little bit because I'm using my. I'm pushing the door with an angle as opposed to perfectly perpendicular to the door. So if you do it perpendicular, if you use your force perpendicular to the door, you're going to open it easily because you will be using your full potential. And also, it matters where on the door you apply that force. So closer to the edge or where it causes the rotation. So you want to do it closer to the edge. It's possible. And well, here is where trigonometry actually describes this. It's pretty cool because, well, so if R and F are parallel, what's the torque? Again, this is the table, this direction. What if my torque goes in the same direction as the table? Am I going to cause rotation? I'm causing displacement, not rotation. So that means R crossed with F, it's going to be equal to the 0 vector, not 0. All right? Again, how can we relate this with the properties of the cross product? Again, because in this case, I'm applying the force. Again, use this table here. I'm applying this force in the same direction as the table. So my force, which could be a stronger vector than the vector describing the length of the table, isn't that just a multiple? They're multiples of one another. What happens when you do the cross product between two vectors that are multiples of one another? You get the 0 vector, isn't it? So that's why there's no torque. Or that explains the fact that there's no rotation, but rather displacement. The question here is, what direction gives the maximum torque? Using common sense, what angle would give us maximum torque? 90 degrees, all right? Let's use calculus to prove this, okay? So again, the magnitude of the torque, which is represented by a lowercase letter tau, that equals, what's that? The magnitude of the cross product between R and F, and the force, and which is the magnitude of the distance times the magnitude of the force times sine of the angle theta. And here is where we analyze the sine function. Well, we don't even need to do any calculus. I mean, you can find the derivative, set it equal to 0, but you don't need it because you know the graph of sine. What angle gives the maximum in the interval 0 and 2 pi? Right? 90 degrees or pi over 2? So you can explain that using the algebra, the calculus, or doing the example pushing the door over there. Either way, right? Let's have a look at one example. Actually, yeah, there's two. Okay, so let R equal to OP be a given vector already that represents some length, all right? And let F be a force that causes some rotation to being applied on P. Find the torque about O that is produced and give its magnitude. So the torque, which is a vector, that is R cross F, right? That'll be IJK. That is 10. Okay, so the R first, it is 1 to 1, and the force is given by 10, 5, 0, and the result for this cross product equals -5, 10, -15. So, but we want to know the magnitude of the torque, not so how much force is applied onto rotating here, okay? So not just as a vector. So we find the magnitude. That is magnitude of tau, that equals to the square root of -5 squared plus 10 squared plus a -15 quantity squared. That equals, what's that? The square root of 350. Okay, so that's how much torque is applied. And one last word problem. This one is another very formulaic. So this time we don't need to compute any cross products, by the way. So a force of 30 newtons is applied to a wrench that is 0.25 meters long on an angle of 60 degrees. So we're going to use the other definition. So the magnitude of the torque right here, that equals the magnitude of the torque times the magnitude of the force times sine of the angle. In this case, we're given everything. Yes. Yeah. Oh yeah, that means I mean R. Thank you, R. Mm-hmm. And in this case, we're not given vectors, we're given their magnitude. So it's going to be a shorter calculation. So that's the magnitude of R, that is the distance 0.25 times 30 times sine of 60 degrees. And using a calculator, we should get about 6.49 newtons meter. Oh, these are the ones that are joules. 6.49 joules. So either one, joules or newtons meter, are both acceptable. Let me make this M look like an M. All right. Very formulaic problems, nothing too crazy. And to wrap up the section, we can find the volume of a parallel pipette, not necessarily rectangular box, but because it could have an oblique side or oblique planes. So, and that's obtained by finding what we call the triple scalar product. So instead of evaluating the triple scalar product, so essentially, in a similar way that two vectors create a plane, three vectors create this solid. All right, so we're going to find the volume of this solid by simply setting up a 3x3 matrix and finding its determinant. So the volume of the box created by these three vectors, simply set it up as a 1, 2, 3, negative 1, 1, 2, 2, 1, 4, and compute this determinant. Again, you can use the shortcut rule, duplicate the first two columns, or use the definition, or alternatively use your graphing calculator. However, on a quiz or an exam, I need to see one of the rules. But you may use your calculator to verify the work. If you don't know how to find the determinant, let me know at the end of the class. So here we get a number that is equal to, oh, I had the, that was, okay, it was quiz. Is it quiz 3? Jesus. Oh, where is it? Where is it? Well, let me do it by hand because I remember doing it before. Okay, here is the one. Oh, that's fall. We're gonna need this file first. Anyway. I think this is the one. No, give me a second. I got 9 units for this, all right? So I get 9 units. In some cases, by the way, you may get a negative number, but because this is a volume, make sure to find the absolute value. Notice how here we have this absolute value bars. So just make sure to find the absolute value again, because there's no negative volumes. And one last piece of information. So three vectors are said to be coplanar if the determinant, like what we just computed before, if it gives us a 0. So in this case, let's determine if these three vectors right here are coplanar. That is, they are on the same plane. In other words, like having this vector, that other vector, and a third vector, they all lie in the same plane. It's not like we have some setting like this. All the three vectors lie on the same plane. That is 1, 4, negative 7, 2, negative 1, 4, and 0, 9, 18. And if we compute this determinant, actually this gives us a 0, which means U, V, and W are coplanar. Right? And